Welcome to the online narrated lectures for CM2101. This week we are going to move on to vibrational spectroscopy. We are going to spend the next 2 weeks discussing vibrational spectroscopy in detail. First, we will look at the instrumentation. Then we're going to look at the simplest molecular system, which, just like for rotational spectroscopy, is the diatomic. We will be assuming that the bond stretches and compresses according to Hooke's law, which is the simplest way of describing the stretching and compression of a bond. Systems that obey Hooke's law are known as harmonic oscillators. Having treated the diatomic as a harmonic oscillator, we will relax this approximation and try to take into account some anharmonicity in the molecule. We're then going to see what happens when we consider vibrations and rotations together. Because remember, molecules are also rotating, so when you excite a transition associated with a change in vibrational state, you will also be exciting transitions associated with rotation. You can't avoid it. Remember the selection rule that delta J, the change in the rotational state, is equal to plus or minus 1. The rotational levels have to change. In part 1 we will be discussing infrared instrumentation and some of the results we see when we do infrared spectroscopy. The most significant difference between the setup of a microwave instrument and an infrared instrument is that the radiation source in infrared spectroscopy is what we call a white source, a broadband source. It is not a monochromatic source as we were able to use in microwave spectroscopy. This means that we are going to have to put in a dispersing element so that we can distinguish between the different wavelengths. So the setup would be that the source of radiation passes through the sample with some of that radiation being absorbed. We know that the sample, once it has absorbed radiation, is going to be emitting radiation in all directions. It is not going to be emitting all the radiation in the same direction as it was absorbing radiation. It will emit in any direction. So for that reason, if we put a detector after the sample, we would see a drop in intensity of radiation at the wavelength at which the molecule is absorbing. We put the modulator in as it will enable us to remove the effect of any stray radiation that might well be in the instrument, or for that matter help to reduce the noise that is associated with the detector. Remember, the amount of stray radiation will presumably be a constant. What won't be a constant will be the amount of absorption that is going on. So if we have a look when all light is stopped and take the difference between the two, hopefully we get the amount of absorption and we manage to reduce some instrumental noise, for instance, or any stray radiation that may well be getting past the modulator. Then we can have an analyzer, and finally a detector. Once we've got enough signal of a particular wavelength, we will tell the analyzer to rotate slightly so we can have a look at a different wavelength. So we can scan through the wavelength range of interest. So what can we use as a white source? We can use a glow bar or a Nernst filament. For instance, the glow bar is a silicon carbide rod heated up to around 1500 degrees centigrade. This emits a broad range of infrared radiation in a virtually continuous spectrum that looks like a black body spectrum. So the spectrum itself, the amount of radiation you'll be getting at any particular intensity, is related to the temperature to which you heated up the rod. The sample can be solid, liquid or gas. I'm sure you have put liquid samples or a Nugol mol between sodium chloride plates, and you may also have analysed a gas sample. Indeed, this is one of the experiments that you do in CM2192, when you'll have a look at the spectrum of gaseous HCl. The analyzer can be a prism, a diffraction grating, or a Michelson interferometer. The detector is essentially measuring heat. In essence, the detector is a thermometer. You can either have a thermocouple, which directly measures the temperature, or you can have a pyroelectric device. Pyroelectric devices are essentially the same thing that you use in detectors in fire alarm systems. Or it can be a Golay cell. In a Golay cell, you've got some kind of casing filled up with a gas which absorbs infrared radiation. So of course, as radiation passes through it, that gas will absorb some of the radiation. There's also a flexible membrane which will allow the gas to change in volume. As the gas heats up, the membrane will expand, so the expansion of the membrane is going to tell you how much infrared radiation it is measuring. This can be an incredibly accurate way of measuring infrared radiation. The only problem is the response time is relatively slow, about 10 microseconds or so. So that slows the process of measuring the spectrum. We do have a further problem working in the infrared, which we don't have when putting together a spectrometer working in the visible region. All the optical components in a visible spectrometer can be made out of glass, but glass is not transparent in the infrared. If I had a pair of infrared goggles on, I would see the amount of infrared radiation everyone is emitting. But if you held a piece of glass in front of yourself, I wouldn't be able to see you at all. You'd be invisible to me. Therefore, we cannot use glass optics. We have to use something that is transparent to infrared radiation. So we generally use sodium chloride or potassium bromide. Most commonly we use sodium chloride because it is cheaper. Potassium bromide is a lot more expensive. So why then would we ever want to use potassium bromide? Well, potassium bromide is transparent to a wider range of wavelengths. So if you need to look at a wider range of infrared wavelengths, you'd have to pay more money and use potassium bromide optics. If you've done the HCl experiment in CM2192, you'll recognise that this is the gas cell in which you put the HCl, and the windows here are indeed made of potassium bromide. The other thing that you would probably notice is that they look quite dirty and scratched up. That doesn't matter so much because you are seeing it looking dirty in the visible part of the spectrum, but it still looks transparent in the infrared. So what happens in this instrument when we fill the sample up with dioxygen or carbon monoxide? Well, our first observation is that we do not get any spectral lines for dioxygen or O2. And in fact, for any homonuclear diatomic, you cannot get an infrared spectrum. We only get a spectrum for a heteronuclear diatomic. So what does an infrared spectrum look like for a heteronuclear diatomic? Well, it depends. Here we have carbon monoxide dissolved in carbon tetrachloride. And we've got a spectral line centered at around 2169.8 wave numbers. Notice that it is about 14 wave numbers different from the value that we calculated from the rotational spectrum of carbon monoxide when we use the expression relating the vibrational frequency to the rotational constant and the centrifugal distortion constant. So you're probably not surprised to learn, therefore, that this is a pretty good harmonic oscillator. There is not a great deal of anharmonicity in this system. Carbon monoxide has a quite deep potential well, which we'll be discussing later. But this spectral line is a fairly broad feature. The peak is at 2170 wave numbers, but it is quite a broad spectral line with a width of several hundred wave numbers. Notice the difference in magnitude of numbers we are dealing with in comparison with the rotational spectrum. In rotational spectroscopy, we were talking in the order of tens of wave numbers. Here, all of a sudden, we are talking about thousands of wave numbers, and the spectral feature itself spans several hundred wave numbers. If we look at carbon monoxide in the gas phase, but the instrument itself is a low-resolution instrument which is averaging over a wide band of frequencies, then this might be the kind of spectrum we would see. Here the spectrum appears to be centered at a slightly lower frequency than 2170 wave numbers. But rather than a single band with one wavelength, we've got two bands appearing with a minimum in the center. The distance between the peaks of these two bands is about 55 wave numbers. So in the gas phase, our peak is being split into two bands with a separation that is approximately 55 wave numbers. Of course, we have instruments that measure at much higher resolutions. Let's see what happens if we measure at a higher resolution. This is the kind of spectrum that we might see. And you can imagine what would happen if you averaged this spectrum over a range of frequencies. You can probably picture that such averaging would construct the previous low-resolution spectrum of the two separated broad bands. The distance between the two peaks in the low-resolution spectrum would roughly be this distance here. So the next observation is that the bands can further split into two sets of almost equally spaced fine lines. Notice the difference between any two lines is roughly the same. However, closer inspection shows that these lines are getting closer together as you go to higher frequencies. And if you look at these lines as you go to lower frequencies, you can see that the lines are getting further apart. This needs to be explained. There is also some structure down here centered at a slightly different frequency, a slightly lower frequency at some 2100 wave numbers. We saw the same problem for the rotational spectrum for carbon monoxide. This is due to carbon-13 monoxide. So those are the observations. We've got 4 observations that we need to be able to explain during our discussion of infrared or vibrational spectroscopy. We have that homonuclear diatomics give you no spectrum, that if we look at carbon monoxide in a solvent we get a single band at around 2170 wave numbers, that if we look at carbon monoxide gas in a low resolution spectrum, we can see that the band has now split into 2 bands which are separated by roughly 55 wave numbers, and finally that if we look at the band in high resolution we can see that they are split into sets of equally spaced spectral lines. This is the end of part 1 of this week's online lecture. Please continue on to part 2.